Welcome. We are going to be reviewing ionic versus covalent bonding and nomenclature. So we're not going to just simply cover how to name and write the formulas for ionic compounds. We're also going to cover what ionic and covalent bonding actually are. So the workshop outlines will be a good framework for you. And the first question you have to ask are, what are ions? So as you may have already heard in class, ions are effectively just charged particles. They can be positive or negative. And they don't necessarily have to be simply atoms. They can be ions, or they can be rather molecules as well that are charged. So ions, like it says, can be a single atom that has gained or lost electrons, or an entire molecule that has gained or lost electrons. When it is an entire molecule that has gained or lost electrons, we call those polyatomic ions. And there's a list of about 8 polyatomic ions that you're going to want to have memorized. We'll get to those in a little bit. And you of course don't have to write down everything here, but just what those things that'll be most helpful to you. All right. So how are ions formed? Basically, it all comes down to electronegativity, which is a concept you're going to learn a little bit more about in a few weeks. Essentially, attraction of an atom towards electrons is referred to as its electronegativity. Usually this refers to the context of bonds. Now if two atoms are in the process of forming a bond and one has a higher electronegativity, like in this case chlorine, the one with the higher electronegativity will steal electrons from the one with less electronegativity. In essence, these are trying to all be like the closest noble gas. So sometimes if the electronegativity difference is not that big between them, they'll end up sharing the electrons. However, in a case like sodium and chlorine, the electronegativity difference is actually quite large, so it ends up resulting in electrons not simply being shared, but actually being completely taken away. So one of the atoms becomes positive, the other atom becomes negative, and the strong electrostatic charge between negative and positive causes these to stick together in what's known as an ionic bond. So, there we go.
Most atoms don't ride solo. Instead, they bond with other atoms. Now, bonds can form between atoms of the same element, or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now these transactions aren't always so cut and dried. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral, because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus. And the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond. Nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
Pretty interesting, huh? So, let's compare the 2 bonding types. For ionic compounds, what happens to the electrons? What can you tell me? What happens to the electrons for ionic compounds?
In ionic compounds that we have in one metal and one non-metal, they attract each other, and one of them losing and other one is gained.
Exactly. So in ionic compounds, 1 electron is lost to the other atom, or 1 or more electrons. It could be more than 1, right?
Mm-hmm.
1 or more electrons is lost to the other atom. But in covalent compounds, what happens to the electrons? Yeah.
Shared.
They're shared.
Shared.
Exactly. So they're kind of pulled in between the 2. So, and these are always valence electrons, outermost electrons that are either given up or shared. Now, how does this affect the atoms? When electrons are lost or gained from in ionic bonding, what happens to the atoms? Yeah.
Ions
Yeah, they become charged, positively or negatively charged. So the atom that loses an electron becomes positively charged. The one that gains the electron becomes negatively charged. But in molecular compounds, when electrons are shared, what happens to them?
they say the covalent.
They each kind of pull on those shared electrons in kind of a tug-of-war fashion. Each atom gets the benefit of having the electrons of the other atom nearby. And so they can all become like the noble gases. We'll go into a little bit more detail on that in just a bit. So why do atoms gain electrons or lose electrons in ionic compounds? Well, the purpose is actually for stability. So noble gases on the periodic table, and just for this point, I want to actually pull up a periodic table. I'm going to go ahead and pull up a periodic table. But noble gases, oh, actually, I don't even need to do that. I have it right here. That'll work. So noble gases are the most stable of all of the elements. So these are your noble gases. So these numbers of electrons, 2, 10, 18, 36, 54, they're particularly stable. They're particularly perfect. And all of the other atoms want to be like the noble gases in the sense that they want to either gain or lose electrons to be like the noble gases, or they want to share electrons to be like the noble gases. So one of the things you'll notice about the noble gases is that they actually have 8 valence electrons. Although actually that might not be entirely obvious to you yet at this point. But, for example, if you look at, let's say, chlorine. Chlorine has 17 electrons, right? And the closest noble gas to chlorine, the closest noble gas to 17 is 18. So it wants to do what? Gain 1 electron, right? And electrons, since they're negative, that means chlorine's going to have what charge? Negative 1. Exactly. And then likewise, sulfur is going to want to gain 2 because it has 16 and it wants 18, so it becomes a negative 2. Phosphorus, it has 15 and it wants 18, so it's going to be a negative 3. So they're all trying to gain or lose electrons to be like the closest noble gas. Now, in covalent compounds, they share electrons to get a full outer shell, just like the noble gases. But it's not as easy to see how that actually comes into play as being like the noble gases, at least not for a few chapters when we start getting into Lewis structures and such. So what does the bonding look like? Well, for an ionic compound, oppositely charged ions stick together like magnets in a continuous three-dimensional crystal structure. Whereas in covalent compounds, molecular compounds, they form discrete molecules, small groups of atoms that are distinct from one another. So, let's take a little bit of a closer look at ionic bonding.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
Okay. So here's an example of the crystal lattice of sodium chloride. Continuous network. And this is why we can't really talk about sodium chloride or any ionic compound as a molecule. It's also why the formulas that we use for ionic compounds are always lowest whole number ratios, or empirical formulas. The empirical formula is the best we can do with any ionic compound because there is no distinct beginning or end to an ionic compound. It's a crystal of beyond billions and billions of atoms. So that's why we have to resort to an empirical formula. So we call this empirical formula group the smallest combination of atoms a formula unit. Cool. So this is a picture of a giant crystal structure. So writing formulas for ionic compounds can be a little bit tricky, but basically you want to follow these general steps. The first step is identify the ions that are present in the substance, along with their charges. And these can be found pretty easily using a periodic table because, as you kind of noticed before, the pattern is quite consistent. Every atom in this group is all going to want to add one electron, gain one electron, to be like the noble gases. So these are all going to be negative ones. These will all want to gain 2 electrons to be negative 2s. These will all want to be gain 3 electrons to be negative 3s. Well, once you get here, it could either really gain electrons or lose electrons, gain 4 or lose 4, but gaining or losing 4 electrons is really tough. So you don't usually see negative 4 or positive 4 ions. Once you get over to aluminum though, this will lose 3 electrons, you'll get plus 3s. And then of course, these are always plus 2s and plus 1s. There's this odd little group of transition metals in the transition metal area that you will have to memorize. And these do not have multiple charges. This group right here. Silver always has a plus 1. Zinc and cadmium always have plus 2s. And aluminum and gallium and indium also usually just have plus 3s. So there's this nice neat little staircase. 1 plus 1, 2 plus 2s, 3 plus 3s. And that's a really easy way to memorize those particular ions. Because, like in the formula, because they only have 1 charge, you'll not be given a Roman numeral to tell you what the charge is. Okay? So, now the polyatomic ions, however, are a different story. There are 8 polyatomic ions, and you will want to take these down. Well, there's dozens of different polyatomic ions, but the most important ones, the ones that show up the most often, the ones that you're going to be expected to memorize, are either these 8 or derivations of these 8 usually. And they are ammonium, which is NH4 with a plus 1 charge. Hydroxide, which is OH with a minus 1 charge. Acetate, which is C2H3O2 minus nitrate, NO3 with a minus 1 charge. Chlorate, ClO3 with a minus 1 charge. Sulfate, SO4 with a 2 minus charge. Carbonate, CO3 with a 2 minus charge. And phosphate, PO4, 3 minus charge. Like I said, these are the most common. These are the ones that will show up 95% of the time on your test. Now, your professor may require you to know more or less depending upon the professor, but these 8 are pretty much essential. You'll want to have these memorized. And unfortunately, there is no rhyme or reason to these 8. You'll notice, for example, that nitrate has 3 oxygens, but it's a -1 charge. However, carbonate has 3 oxygens, and there's a 2- charge. So the number of oxygens doesn't really tell you anything. You'll notice that chlorate has the same charge as chloride, Cl-, but nitrate does not have the same charge as nitride, which is a 3- charge. So you can't go by the charge of the element by itself without the oxygen. Unfortunately, there's no clear pattern here. It's really something that's a little bit more complex than you're ready to go into now as to why these are the charges that they are. But that's okay, because they're not too bad to memorize. All right, second step. So let's say, for example, if you're looking for the ions, if you have magnesium phosphate, magnesium here is a +2 charge. Phosphate, one of the polyatomic ions I just showed you, is a -3 charge. So as soon as you get the name, you want to identify the ions. Next, find the lowest common multiple of the 2 charges. So multiples are like counting by, multiples of 2 are counting by 2s. So for magnesium, multiples of 2 are like 2, 4, and 6. For phosphate, multiples of 3 are like 3, 6, and 9. The lowest multiple that they have in common, the lowest multiple they both have, is the 6. Once you know the lowest common multiple, determine the number of each ion that is needed to get the charges equal to the lowest common multiple. In other words, how many magnesiums do I need to get a total charge of 6? 3. 3 times 2 is 6. How many phosphates do I need to get a total charge of 6? 2. Once you know how many of each ion that you need, indicate how many of each with the subscript. So, I needed 3 magnesium, so I put a 3 subscript there. I needed 2 phosphates. Now, whenever you need more than one polyatomic ion, you need to put the polyatomic ion in parentheses. And then you can put the subscript outside the parentheses to indicate how many of the polyatomic ion you have. A common mistake that students sometimes make is they cut off the last number of the polyatomic ion, the PO4, they cut off the 4, and they just put PO2. You've got to make sure that you put the PO4 parentheses 2. All right. So, let's try a few practice problems. Go ahead and take a moment to come up with the formulas for calcium bromide, aluminum oxide, and zinc nitrate. Oh, and you'll probably need a periodic table, which I'll go grab you some. Does anybody need a periodic table? Here you go. Welcome. You'll be given one for the exam, but I don't know exactly which one it's going to be.
Ah, okay, so it's similar to this one.
Yeah.
The lab manual. Check it.
We're identify the ion. Identify the lowest common multiple. And figure out how many of each ion you need. The key trick to this is to recognize that the total number of positives always has to be equal to the total number of negatives. You got it?
Yes. Okay.
All right, let's take a look at the answer sheet. So you should have gotten CaBr2, aluminum oxide, Al2O3, and zinc nitrate, ZnNO3, 2. Does anybody want to go over how we got those?
Yeah.
Yeah.
Yes? Okay. So, I redirect my little camera here. Bum, bum, bum. And so for calcium, calcium's C8 and has a 2+ charge according to the periodic table, right? And then bromine has a -1 charge according to the periodic table. It's one away from the noble gas. So if calcium has a 2+ and bromine has a 1-, the lowest common multiple is what? So multiples of 2 would be like 2, 4, 6. Multiples of 1 would be 1, 2, 3, 4. So what's the lowest common multiple?
2.
Yeah, exactly. You got 2. So notice something really interesting here. Okay? Since it's the first multiple of calcium, you only need 1 calcium, right? 1 times 2 is 2. And it's the second multiple of bromine, so 2 times 1 is 2. I need 2 bromines. The lowest common multiple is 2, and which multiple it is tells you how many you need. If you throw it like this, I mean, you could also just recognize, oh, the lowest common multiple is 2, and so what times -1 gives me -2? Well, 2, right? And there you go. Now let's take a look at aluminum oxide. So for aluminum oxide, aluminum has a charge of what? Yeah, so aluminum's a 3+, and oxygen is a 2-. So the lowest common multiple of 3 and 2 is? What? 6. 3, 6, 9, 2, 4, 6. 6 is the lowest common multiple. I need how many aluminums then?
2.
2. And how many oxygens?
3.
And then, last but not least, zinc nitrate. So, grab my eraser, and I will erase this. And Zn is one of those tricky ones you kind of gotta know that it's going to be a negative or a positive 2. Nitrate's also a polyatomic ion you gotta memorize. So the lowest common multiple of 2 and 1 is 2. How many zincs do I need then?
1.
1. How many nitrates do I need? So I put an NO3, 2. Now, one important note. Yeah, when you have more than one polyatomic ion, make sure you put the parentheses and the subscript after it. Subscripts tell you how many atoms you have. Whereas superscripts tell you the charge. They are not the same. They do not tell you the same things. Now, that said, your teacher will probably try to teach you what's known as the crisscross method. And they'll say, just cross the charges, okay? And while that usually works, it doesn't always work. And you'll also have to keep in mind that this 2 is not here because oxygen's charge is 2. This 3 is not here because aluminum's charge is 3. This 3 is here because you have 3 oxygens, and the 2 is telling you have 2 aluminums. That's what the actual 2 and the 3 mean. Now, it's because of the charges that you end up having these ratios, but it's not necessarily a guarantee you cross the charge you're going to get the right formula. Let me give you an example. So, let's say you have something that has a 4+ charge. Let's say something like this. Let's have lead. Lead can have a 4+ charge. And let's say you combine that with sulfate, which is 2- charge. So now, if you just cross the charges, you get Pb2SO4, right? But if you did it the lowest common multiple way, what's the lowest common multiple of 4 and 2? 4, 8,
Oh, cotton multiple.
2, 4, 6. So yeah, it'd be 4, right? So that means you need how many leads?
4.
4?
2.
1 lead. 1 lead to get positive charge of 4. Plus it's the first multiple, right? And how many sulfates do you need to get a charge of 4?
2.
2. So you got SO4, 2. So that's the formula for that. Notice crossing would not give you that. So if you're going to use crisscross, just be careful because it can bite you if you're not careful. Alright, let's do some naming. So for naming, it's a little bit trickier in some senses. In some sense, it can be easier. You name the cation first. So for a metal cation, it's named the same as the element. For a so like for example, if you see that the ion is Al3+, or if you have a formula like Al2S3, well, I can just say aluminum. Name the metal exactly the way it is. If it's a metal cation. However, if the metal can have multiple charges, like a transition metal, then you must indicate what the charge is with a Roman numeral. So the transition metals are those elements in the middle of the periodic table. The elements in the middle of the periodic table. Essentially, transition metals are everything except those first 2 columns on the periodic table and that little triangle of elements I showed you. So like for example, since lead is a transition metal, if you had a 4+ charge with it, it would be lead with Roman numeral 4. Or copper with a 1+ charge would be copper 1. So after you name the cation, then you name the anion. Now if it's a monatomic ion or a single atom ion, you have to change the ending to IDE. Usually it's the first syllable followed by an IDE ending. So oxygen becomes oxide. Chlorine becomes chloride. Nitrogen becomes nitride. Phosphorus, phosphide, and so forth. For polyatomic ions, there actually is no change in the name. You can actually just write it exactly the way it is. So chlorate, sulfate, carbonate, etc. No need to change the name. Alright, so let's try some of these. Let's name them. Take a moment to name these 4 compounds. I'm sorry? Sorry? Yeah. Sorry.
No, I was trying to figure out the names.
Oh, gotcha.
Yeah.
Alright. Who wants to give us the name for number 1?
Aluminum sulfate.
Aluminum sulfate. What about number 2?
Ammonium sulfide.
What would you say?
Ammonium sulfide.
Ammonium sulfide. Very good. Number 3?
Zinc oxide.
Zinc oxide. And number 4?
Silver hydroxide.
Silver hydroxide. Very good. Aluminum sulfate, ammonium sulfide, zinc oxide, silver hydroxide. In none of these cases did you have to use transition metals. Now, writing names for compounds with transition metals is a little bit trickier because you got to figure out what the charge of the transition metal is when you see the formula. So, you have to. The first principle is that the total amount of negative charge is going to be equal to the total amount of positive charge. And once you calculate first how much total negative charge you have, so look at your anion, figure out how much total negative charge you have. That amount is going to be equal to the positive charge. Step 2, divide the total positive charge by the number of transition metals you have to get the charge per transition metal. And then you can write the name of the compound indicating the charge with the Roman numeral. So, as you see here, you have iron sulfate, or FeSO4 but we don't necessarily know the charge just by looking at this. So each sulfate ion has a negative 2 charge, and since there are 3 of them, the total negative charge is negative 6. That means there must be a 6 positive total charge as well. Since there are 2 irons, I divide that 6 total positive charge by the number of iron ions, and that gives me a +3 charge per iron ion. Therefore, I would call this one iron 3 sulfate. Iron Roman numeral 3 sulfate. Does that make sense? Any questions? All right. Shame on me. I forgot to turn it around. Whoops. Okay, so let's practice. Let's do a few of these. Let's go ahead and write the names of each of these compounds. Cadmium. It's out here. Yeah, no problem.
Yeah.
Negative ion first. So there's 3 of them, right? Each one has a charge of what?
4.
Actually, sulfate's polyatomic with a negative 2 charge. So you have 3 times negative 2, which is
6.
negative 6, which means the chromiums have to be
Positive.
positive 6. So instead of 2 chromiums, each one must be how much?
3.
3. So chromium 3 sulfate.
1.
No, that's not magnesium, that's manganese. You need Roman numeral. Other 2 are right. be the charge if it's
Solution.
Yep.
It's
All right.
two.
Let's take a look. See how many you got. All right, you should have gotten chromium 3 sulfate for number 1, iron 2 carbonate for number 2.
Yes.
Cadmium is actually a constant. It's one of those little triangle of elements, so you don't need a Roman numeral for that one.
Mhm.
That would just be cadmium hydroxide. And then the last one is manganese 4 oxide.
Oh, four.
Are there any of those that you'd like to go over?
Yeah, the last one.
The last one, manganese
Oh.
4 oxide?
Oh.
Okay. So, redirect my little camera here. There we go. Increase the lighting a bit. Alright, so basically, for manganese 4 oxide, first of all, manganese is Mn, and then oxide, of course, is O with the 2 minus charge, right?
Yes.
And the formula is given as MnO2.
Okay.
Okay. I don't know what the charge of manganese is, but I know that I have 2 oxygens, each one with a -2 charge. So what's the total negative charge here?
4.
-4. If that's the case, what's the positive charge that manganese must have? +4. So since there's only 1 manganese, that +4 is due to that manganese, so this would just be manganese 4 oxide. Now there's a reason that I chose to do this particular workshop. Naming and writing ionic and covalent formulas is one of those things that people kind of assume is sort of easy, and for some people it is, but for most students it's a little bit tricky because you're mixing up math with letters, and it kind of throws a lot of people off. And I find a lot of my chemistry 1411 students struggle with writing and naming ionic and covalent compounds even well into Gen Chem 2. Like they're still making mistakes. If you get this down now, you'll save yourself a lot of headaches later. Alright, so any of the other ones you want to go over?
The second one.
Yeah.
Oh, yeah, the second one.
I'm sorry?
The second one.
Second one? Iron 2 carbonate. Okay, so carbonate. So iron 2 carbonate, you see FeCO3. So the CO3 here is a polyatomic ion. And by the way, anytime you see more than 3 elements in a compound, chances are you probably got a polyatomic ion. So, iron 3 carbonate. So the carbonate has a -2 charge, and there's only one of them, and there's only 1 iron. So if the total negative charge is a -2, the total positive charge has to be +2. And therefore this is going to be iron 2. And let me emphasize this because this is also a common mistake that a lot of students make. Iron 2 does not tell you you have 2 irons. Iron 2 tells you the charge of iron. Just like manganese 4 does not tell you you have 4 manganese, it tells you the charge of manganese. Those Roman numerals tell you the charge. Okay. Let's go to covalent compounds. Fortunately, covalent compounds are a little bit easier. Binary covalent compounds is all you're going to be worried about doing the names of. So, for binary covalent compounds, because covalent compounds can basically have multiple combinations. In other words, for example, you can only have ionic compounds in one particular way typically because they're only going to lose a certain amount of electrons and other atoms are only going to gain a certain amount of electrons. So you're pretty much stuck. It's like you're either going to gain, like oxygen's just always going to lose or gain 2, and magnesium's always going to gain 2, so you're always stuck with MgO. However, covalent compounds aren't limited like that. They can actually combine in many, many different ways. So for example, nitrogen and oxygen, what I'm going to write down are all legitimate compounds of nitrogen and oxygen. So you can have NO, you can have NO2, you can have N2O, you can have N2O4, and you can have N2O5. All of these are actual compounds formed with nitrogen. None of them have anything to do with the charges. So, it's because when you share electrons, you can share them in a lot of different ways. In this case, because there's no way to predict how many you're going to have with charges, you have to indicate with prefixes how many you have when you name it. The prefixes go before each one. So to name a form of covalent compound, all you do is name the first element with its appropriate prefix. Unless, of course, the prefix is mono, you never use mono for the first element. So for example, I would not say mononitrogen, but I would say dinitrogen for N2. Now, the second consideration, you name the second element with the appropriate prefix, but you also have to change the ending to IDE. So, I wouldn't put a mono in front of the nitrogen, but I would put a mono in front of oxygen. So this would be nitrogen monoxide or nitrogen monoxide. And this would be nitrogen dioxide. I changed the ending to IDE. This would be dinitrogen monoxide, and this would be dinitrogen tetraoxide. Except when you have oxygen, you do drop the A. You do drop the A. Normally you'd say, oh, it would be tetraoxide, but it turns out that whenever you have oxygen, you drop the A, and it's just tetroxide. Kind of like one of those weird rules. Fortunately, like I said, this is it's pretty easy to pick up with a little practice and you'll have it down. Let's have you practice naming these compounds using their appropriate prefixes. Like that. All right. Let us see how you've done. What did we get for the first one? Carbon dioxide. That's probably one you already knew before looking. What about this one?
Dinitride, dinitride,
Dinitrogen?
dinitrogen, trioxide.
Pentoxide.
Pentoxide. 5 is
This is
penta,
five,
so
okay.
dinitrogen pentoxide. What about number 3? Go ahead.
Tetraphosphorus decoxide.
Decoxide. Tetraphosphorus decoxide. And what you have number 4?
No. I had number 3.
Sorry.
So dinitrogen oxide.
Dinitrogen what?
Oxide.
Monoxide.
Monoxide.
Monoxide. And what about the last one?
Triphosphorus iodide.
Not quite.
Phosphorus triiodide.
phosphorus triiodide. So it's weird. You know how we dropped that A for oxide? We don't drop the I for triiodide. It's really weird. You actually have two I's. It's kind of weird looking. The O is the only one we drop letters for. So carbon dioxide, dinitrogen pentoxide, tetraphosphorus decoxide, dinitrogen monoxide, and phosphorus triiodide.
So when do you add the IDE?
You add the IDE to the second element, and typically it's after the first syllable of the second element. So you add, so there's the prefix, okay? And now for, normally it would be oxygen, right? But you take the first syllable, ox, and then you add IDE, oxide. Or in the case, oh, these are all oxides, oh, whoops. Or like in this case, iodine is one of those little weird exceptions. You actually do two syllables, iodide. So, otherwise it's normally like fluoride, bromide, phosphide, nitride. Iodide is one that has two, and selenide is one that has two. But other than those two, typically you just take the first syllable and add IDE. All right, so at this point, we have gone over naming and writing each of these. So let's go ahead and switch gears and do some mixed ionic and covalent naming and writing. So let's do some mixed ionic and covalent naming and writing. First trick, how do you tell it's ionic versus covalent? It'll be ionic if what? Yes?
It'll be ionic if there's a charge or if there's like more than two elements charged.
Well, you're right. If there's more than two elements, it will be ionic, but what's an even easier dead giveaway?
You should have known which one is metal or non-metal.
Yeah, ionic compounds usually have a metal, right? So ionic compounds usually have a metal, whereas covalent compounds are only composed of nonmetals, right?
Yes, non-metal.
So let's do a couple of these together, and then I'll send you off to practice some on your own. All right, so let's take a look at the first one. Number one. Is that ionic or covalent?
This one is
What's Ni?
Nickel.
nickel.
Nickel. Is that a metal already?
Yes.
Yep. So that'll be ionic, right?
Ionic.
So it's an ionic compound. So second question you ask yourself, is Ni a transition metal? Yes, it is. So that means its name needs what?
Non-normal.
A Roman numeral. So let's figure out what the charge of Ni is. How do we do that?
You just check sulfur's the second charge.
Yeah, you check the charge of the anion. So sulfur has what charge?
-2.
-2. And since there's only one of each, that means nickel has to be what?
2.
+2. So Ni is a -2. So because positives are equal to negatives, nickel has to be a +2. So this would be what? How would I name this?
This is sulfide nickel.
What's
Nickel
that?
sulfide.
Nickel 2 sulfide. Nickel
2 sulfide.
2 sulfide. Excellent. What about number 2? Is that ionic or covalent? Ionic. How can you
Ionic.
tell?
Because manganese.
Manganese is a metal, right? Mn is a metal. You can look on your periodic table and you can see that it is on the metal side of the periodic table. So is manganese a polyatomic ion? Or rather, is manganese a
Yes.
transition metal?
Yes.
Yes. So what does it need?
Roman.
Okay. Roman numeral it is. MnSO4. Now what's this SO4?
Polyatomic ion.
Polyatomic ion. What's its name? What's its charge?
Sulfate, -2 charge.
Sulfate with a 2- charge. So we have sulfate with a 2- charge, and that means manganese has what charge? +2. Because there's only one of each, right? So this would be
Manganese two.
Yeah, manganese 2 sulfate. Excellent. What about number 3? Is it ionic or covalent?
This one is a covalent
How can you tell?
because of S.
They're both
Non-metals.
nonmetals. Alright, so they're both nonmetals, it's covalent, which means we're not going to use ions. What are we going to use?
The
So,
prefixes.
Prefixes. And so what would the name of this compound be?
trifluorine
Yeah, trifluorine
chloride. Tetra.
tetrachloride. Trifluorine tetrachloride.
So would you only use the the prefixes on the nonmetals?
Exactly. Well, no, yes, you only use the prefixes on the covalent compounds. The covalent compounds, so for example, I would never use a prefix for an ionic compound. It doesn't matter how many S's or whatever I have. I only use prefixes for covalent compounds. For ionic compounds, it's the charge that tells me how many of each I have. So to that end, let's go ahead and let's do a couple of the writing formulas ones. Let's start with number 21. 21, barium hydroxide. What's the first thing I want to do if I'm going to write the formula for that?
BR.
Isn't Br as well?
What's barium? Is that-
Metal.
It is a metal. So it is, what type of compound?
Ionic.
Ionic. And what is the symbol for barium? Ba. And what's the charge of barium?
Plus two.
+2. It means to lose 2 electrons to be like the closest noble gas. What is hydroxide?
-1.
It's a -1, but what is it?
What?
Polyatomic ions, OH, right? So, how many bariums and how many hydroxides do I need in the formula?
One barium, 2 hydroxide.
That's right. It's the lowest common multiple of 2, so I need only 1 barium to get a charge of 2 and 2 hydroxides to get a charge of 2. And so it's BaOH parentheses 2. Don't make the mistake of writing this. Don't do this. Do not do that. Because then you haven't doubled the whole recipe. Think like you're baking a batch of cookies, but you only doubled the flour. That's not going to be a great batch of cookies, right? Got to double everything else. So, polyatomic ions, you got to double everything. So you need to put them in parentheses if you have more than one. Alright, let's take a look at number 26. Disulfur trioxide. What type of compound is that?
Covalent.
Covalent. Can automatically tell because of the prefixes or the fact that they're nonmetals. So what would the formula for disulfur trioxide be?
It is S2 3 O.
S2O3, right? S2O3, very good. All right. Let's, if anybody wants to continue to work on this, I'll kind of go around and let you guys work on it together. I guess we have a few more minutes. It's kind of done, but if you want to leave, it's cool. But if you want to keep working on it, I can check and see if you really got it down. All right? Cool.
Thank you, Mike.
You're welcome.
Thank you.
Thank you for coming.